Let's look at another example. In this circuit, we again want to find a V0 of t, but now we're given that the initial value of V0 is 5 volts. So V0 at 0 is 5 volts, and we see that is our capacitor voltage. In this case, we see that our circuit does not have any switches, but rather our sources are explicitly defined with, in this case, our voltage source on the left, a step function u of t, and on the right, our current source has a delta function d of t. And so what that might represent is a momentary current spike that comes from some switching operation. So, like with our last example, the first step here is to transform our circuit to the S domain. So transform our circuit to our S domain. So let's do this one component at a time. So of course for our resistors, we don't see any change. So resistors, no change. There's still going to be 10 ohm resistors in our S domain. For our voltage source on the left, so we have 10 e to the minus t u of t, and so we can realize this by seeing we have a constant 10. We have this e to the minus t, which corresponds to a shift in frequency. We know that our u of t goes to 1 over s, so putting all of these things together, so basically using our table for Laplace transform pairs and knowing certain operational properties or operational transforms, we have that this goes to 10 divided by s plus 1, and the units of that would still be volts. Now for our other source on the other side, we have 2 delta of t, and so our Laplace transform of delta is just 1, so this just goes to 2 amps. So finally, we have our capacitor. So our capacitor is a 0.1 farad capacitor in our time domain, and we know that we have a 5 volt for our initial conditions. So our impedance is then going to be 1 over SC. So plugging in the 0.1, we get 10 over S, but because we have that initial conditions of 5 volts, this 10 over S is going to have to also have a voltage source in series. And so that voltage source value is going to be a voltage source of 5 divided by S volts in series. Or we could also choose to have a current source in parallel. And so our current source value would be 0.5 amps in parallel. And so one thing to keep in mind with this voltage value, so we have this voltage and this current here. So I've specified that our voltage is in series and our current is in parallel, but we want to be very careful about voltage polarity and current direction. So careful with our voltage polarity. Well, let me not say and, because we're only going to use one or the other. So our current direction. And so a good idea is maybe if you want to pause the video and try to write the circuit out yourself, making one of those choices, or write it out with both and see how it looks and see how that would change the analysis type that you want to do. So, of course, the obvious question then is which one of these two do we want to do? Do we want to do the voltage source in series or the current source in parallel? And so the answer is that it doesn't really make a huge difference, particularly for this circuit. So what we're talking about is we're going to replace this capacitor with a capacitor and a voltage source in series. So what that would look like is, of course, we'd have our capacitor. So we'd have something like this. So we'd have our capacitor and our voltage source. And I'm not sure off the top of my head the polarity, so I don't want to draw that in incorrectly. Alternatively, we could have our capacitor in parallel with a current source. And again, off the top of my head, I don't want to mess up that current direction, so I'm not going to include that there. But let's just say this is our current, so let's say this is amps and this is volts. So in this case, we can see it's not going to make a huge difference. If we do the current source method, or not the method, but if we have our current source, we could combine the two current sources in parallel, so that could be an attractive option. But what we're going to see is that, again, for this circuit, probably node voltage is going to be our easiest method. So it's not going to make a huge difference. Both of these are going to be about the same in terms of doing node voltage analysis. But let's go ahead and use this one. That way we're going to be dealing with this 0.5 as opposed to having this 5/s voltage floating around. But again, you can choose whichever one you want, and you should get the same answer regardless. If you want to try that, or if you want to see me work through that, let me know and I'll be happy to either check your work or help guide you through that. So just rewriting our circuit here, we have our two resistors, which are unchanged. We then have our capacitor, which is going to be replaced by the capacitance in parallel with the current source. So that's sort of the option I've chosen here. And so again, checking with the notes, we would check our notes for our capacitor transform, and we would know that this current source has a direction pointing upward. And then we also have this current from our 2 delta, which in our time, or in our S domain, is going to be just 2s. So we get something that looks like this. So the value of this voltage source we said was 10 divided by s plus 1. We have two 10 ohm resistors. Our capacitor has an impedance of 10/s. Our current source from our capacitor has 0.5 amps. And we have a 2 amp source here. And this is our V0 of S. So one thing to note, if we had chosen this voltage source in series with our capacitor, the voltage V out of S would be across both of those things. So remember, this would be our V out of S here, as opposed to, in this case, it looks something like this. Okay, so again, as I mentioned, we could combine those parallel current sources and just make that a 2.5 amp source. It's not really necessary. It's not going to change things too much. So let's go ahead and look at how we could solve this with our node voltage method. So again, the reason I say node voltage method is, again, we see we have two essential nodes, so n sub e equals 2, which means we are only going to need one equation. In this case, mesh current, let's say we had combined these two current sources, that would give us 1, 2, 3 meshes. So we'd have m equals 3, which means 3 equations. We could also, of course, still do parallel combinations of impedances and source transformations. Simpler steps, but more of them. So it's kind of just a pick your poison sort of thing. So let's again look at our node voltage, and I promise in later examples we'll look at some mesh current and some other techniques. So let's choose our bottom to be our reference again, and our top to be our node of interest. And between the two, we then have V1. So another reason that our node voltage method is sort of attractive here is because we notice that V1 is equal to V out. And so what that means is once we solve that node voltage equation, we immediately have what we're looking for in the S domain. So these are the kind of things that you want to be considering as you're choosing which analysis method to use. And again, there's not necessarily a right way. Sometimes there might be a quicker or an easier way, but if you prefer to do it another way, then by all means do that method. Okay, so we're going to write our node voltage equation at that node 1. So we're going to be tracking our current. So again, we're going to have a current here, going down here, down here, down here, and out to the right here. And so writing each of those, what we're going to have is out of the left, we have V out minus 10 over S plus 1 divided by 10. And so note I've gone ahead and I'm just using V out instead of V1. And let me move that down a little bit just so we're not too close to that previous line. So the next current going downward through the 10 ohm resistor is V out over 10. Going down through that capacitor, we have V naught over the quantity of 10 over S. And then we have our two current sources, which is going to be negative 0.5 and negative 2. And that's everything, so we set that equal to 0. So the easiest way to deal with this, we see we have a 10 in the denominator, in all of these fractions, so let's just multiply everything by 10. And so that's to get rid of these denominator terms here, so this 10 is going to cancel out here, here, and here, and then we're going to have 10 times these two terms, essentially. Okay, so doing that, what we have then is we're going to have and sort of collecting some terms, we're going to have a v naught from that first term, plus a v naught from the second term, plus an s v naught from the third term, and then we're going to have a -5 and a -20. Moving them to the other side, we have +25. And then also on the other side, we have our other term, which didn't contain any v out term. And that's going to be our 10 over s plus 1. So moving that to the other side, we get plus 10 over s plus 1. And so I can find a common denominator for these of s plus 1 to simplify this a little bit and say that this is 25s plus 25 plus 10 over s plus 1. So I can write it as something like this. So then let me come back here to the left side and let's sort of factor out this v naught from everything. So this is v naught times s plus 2, and this is equal to our 25 times s plus 35 over s plus 1. So I've just combined these two terms here because they have a common denominator. Okay, so of course now I can just divide both sides by this s plus 2 to get that our v naught is equal to, we're going to have s plus 2 times s plus 1 in the denominator and 25s plus 35 in our numerator. And so of course what we can do now is we can use our partial fraction expansion. So we can say this is going to be some constant k1 divided by s plus 1 plus some constant k2 divided by s plus 2. And so of course our goal with our partial fraction expansion is to be able to get this into some simple form, and then we can just use our Laplace transform table. So solving for that, and so let me keep that on the screen there, we can say our k1 using our residue method is 25s plus 35 divided by s plus 2 evaluated at s equals -1. So we have the case 1 we looked at in partial fraction expansion, so real and distinct poles. And so evaluating, plugging in -1, we see this is just 10 over 1, which is of course equal to 10. And then for k2, we have 25s plus 35 divided by s plus 1, evaluated at s equals -2. Plugging in, we get -15 divided by -1, which is of course just 15. So now, looking at this and knowing our k1 and k2 values, we can inverse transform, and we can say that our v naught of t is equal to 10 e to the minus t plus 15 e to the minus 2t, all of that times our unit step function in units of volts.